Okay, thank you so much. So in this session, we are going to cover what is the fault simulation. We'll be covering what is the fault simulation and what are different techniques to cover the fault simulation. After that, we'll go for combinational circuit testing. Combinational circuit testing will be the next one to create the ATPG, how we have to proceed. That will be the next topic in this talk. So fault simulation, basically the fault simulation is used to evaluate the quality of a test set, usually in terms of fault coverage. For example, yesterday after fault collapsing, in one of the case we found 4 by 16. Okay, so it means we are able to cover 8 out of these faults. 8 we were able to cover just by reducing it. Okay, so that is the reduction. Likewise, let's say I have a test vector and I am able to cover 2 faults out of those 6 faults. So the coverage will be 33%. So likewise, we have to evaluate the quality of test sets so that we can figure out how much coverage is possible to incorporate into ATPG for automatic test pattern generation so that we can reduce the complexity to construct the fault dictionary so that for post-test diagnosis we can figure out that which fault is covered corresponding to which test vector. As I told you yesterday, there are few test vectors with the help of which we can cover multiple faults. So basically, this is the concept of fault simulation, how it is done. First of all, we will be having the test patterns. These test patterns are applied to the circuit. First of all, it is applied to the fault-free circuit so that we can have the reference or the golden output. So the output of this will be the golden output. Then how many single stacked faults are possible in that particular circuit? So we will be considering a single stacked fault at a time. Single stacked fault, actually yesterday we have discussed that single stacked fault is going to cover multiple stacked faults altogether. So we will only cover the single stacked faults, and that too if we are having using the checkpoint term, we figured out that only at the inputs if we have the faults, then it will be okay. We will be able to cover most of the faults if these are reduced to the input faults and the fan out branches only. So yeah, so what we are going to do is at a time we will be taking one fault and we will create according to the test site fault sites, we will be creating the multiple copies of the faulty circuits. Then the same test pattern of vectors will be applied to each and every one. Every circuit will be compared with the golden reference. If there is any mismatch, it means that particular fault corresponding to that test sequence has been detected. So that particular test, the input vector is the test pattern for that particular fault. So this is how the concept of fault simulation is. So there are some basics for logic simulation. For fault simulation purpose, mostly the gate delay we will be assuming 0. Gate delay we will be assuming 0 unless until we are not using the delay faults. So here we will only consider the logical faults stuck at 0 and stuck at 1. So we will presume the logical values attained by any of the branch are 0, 1 and don't care, that is x. So 0, 1 is one of the logical value, one set of logical value, and don't care, we do not know about what value it could be. So these are the 3 values we will be taking. There are 2 types of simulation mechanism. One is the obvious code compiled algorithm we can have, and another one is the interpretive event driven. How it works? So this one is the compiled code algorithm. Here you are going to load each and every input, each and every branch you are going to load in your program, and then you are going to figure out that what will be your output corresponding to these inputs. And yeah, so the complexity of fault simulation depends on the pattern, how many patterns you have been using, how many gates are there in that circuit, and how many faults are available. So basically it becomes G3 complexity is G3. So it is very much complex. Fault simulation is very much complex algorithm. So in this, the characteristics of the fault simulation is shown. There is a diagram. F1, F2 are the faults. So fault activity with respect to the fault-free circuit is often it is sparse matters in time and space domain. In this example, there are two faults F1 and F2. So these two faults are not having anything common as such the branches are considered. So if F1 is not activated by the given pattern, for example, in this case, we have 0 at the input and we another input is 1. So 0 1 combination gives you 0 over here, but the fault was stuck at 0. So it means this is not being activated and this is being activated. So the output here becomes 1. We are expecting that output is 1, but because of the fault it is 1/0. 1 is the true and /0 means it is the faulty output. And now it is going to the next level of the circuit. So since here we have not activated it, so irrespective of whatever this could be, the output will remain 0. So we are not able to figure out any one of the pattern. In this case we are not able to push any of the fault at the output. If we are not able to push any of the fault at the output, it means that fault is non detectable. We are not able to detect that fault. So basically there are uh, some classical fault simulation techniques, and these are listed over here. There are 4 classical techniques. One is the very trivial technique, which is the serial fault simulation technique. Serial fault simulation technique means every fault you will consider once, and at a time you will work for a single fault. Another one is the parallel fault simulation, deductive fault simulation, and concurrent fault simulation technique. So these four techniques, parallel, deductive, and concurrent, these will be taking multiple faults altogether into consideration, right? So parallel fault simulation technique, let's say you are having 3 faults altogether you can simulate. So you will be taking care of 3 faults at a time. So what is the difference between, let's say, a serial fault and the parallel fault simulation technique? Let us have it. Parallel fault simulation, serial fault simulation we'll consider first, and then we'll go for the parallel fault simulation. So in the serial fault simulation, for example, let's assume this is a circuit. This is the circuit. So in this circuit, I want to detect 3 faults out there. I want to detect this, and this with the help of serial fault simulation technique. What do I need is, first of all, I need one is fault free and one is faulty. So fault free is 1. Let me represent it by this, and this is for the faulty. That can be in the first pass it can be, let's say, F0. Another pass it can be B1, another pass it can be J0. So I have to run this 2-bit set memory space I require, and there are total 3 pass are required. 3 pass are required because there are 3 faults, and at a time I can only actually work with 1 fault. So 3 pass are required, and in 1 pass at least 2-bit space is reserved for every branch. I have to put my input over here in the 2 set of bits. Likewise, I have to put my input over here in the 2 set of bits, and like that. So for example, let me take it like this. So for example, I have taken B1 fault in this particular. Yeah, so if I'm going to take the B1 fault in this particular, so B1 is the stacket 1. So it means to activate that fault, just opposite of that I need to put. So this is the activation. Okay. So yesterday we have discussed the controlling and non-controlling. So controlling input is the input which controls the output. For example, for AND gate, what is the controlling input? If I'm having one input 0, I don't care about the next one. I will be getting 0. I will be getting 0, yes. For OR gate, if I have 1 at one of the inputs, so I do not care about another of the input, and irrespective of that, I will be getting 1 at the output. Okay, so the controlling input for AND gate and NAND gate, it is 0. For OR gate and NOR gate, it is 1. Controlling input is 1. And other is non-controlling. For example, instead of 0, if you are going to apply 1 at the input, then it really matters what was the input to the other branch. Let's say I have applied 1 over here. What will be the output? So output will be decided by 1 into whatever the other branch. Let's say B is the other branch. So 1 ended with B. This is the output. So B is going to control now, because 1 was the input which was non-controlling. So B is the one which is going to control. Likewise, for OR gate, if I'm having 0 input over here and this is my B input, so the output will become 0 plus B. So it means if B is 0, the output is 0. If B is 1, the output of OR gate becomes 1. So we have to take into consideration the controlling and non-controlling, so that we can properly pass the fault at the output. So first we are going to discuss the serial fault simulation technique. So in the serial fault simulation, as I told you, one after one we can take. So first of all, I'll be taking, see, this is stuck at 1. So this is to activate this, I have to apply 0 over here. So basically this is 0/1. This is the standard way to present how the faulty and non-faulty value is. So 0 is the true value and 1 is the faulty value, because the B is stuck at 1. We are not considering any other fault available in the circuit, because at a time I can have only one fault altogether. So since the fault is happening at the B branch, so we are going to start with the 0. So we will be having two sets of this. At B branch, when I'm looking over here, what I'll be having, I will be having 0, which is the true. Okay, true, I'm going to take, let's say, first I'm going to take the fault free and then faulty. B/1, that is faulty. So the next one is 1. Likewise, I'll go for the next one. Does it really matter that what was the f value if B was stuck at 1 and there was no fault at f? No, it really doesn't matter. So if the 1 is the input, whether B is having faulty value or not, I will be having another value also, 1 over here. Let's go over here at C. If I'm going to C or D, then since this is the fan out, C and D are the fan outs, so whatever the faulty or non-faulty was at B, the same is propagated. So I'll be having 0, 1 here. Likewise, this is also 0, 1. If both the value is 1, the faulty value becomes 0. So these are the two bits. Now, see, I have taken this fault, right? B is taken, one fault I have taken. What is my job? My job is to propagate this fault towards the output. So how I can propagate? I have two ways to propagate this, two paths to propagate this. What are those two paths? So first path, you can propagate through this gate and then you can reach over here. Another path is you can take this path and you can propagate over here. You may choose both of the paths or any one of the paths you may choose. Okay, so let us consider one of the path. So whatever path I'm going to choose, I have to make sure that the effect of the erroneous input has to propagate through that particular gate. So what type of input I have to apply for that gate? I have to apply the non-controlling value. So let us consider that I'm going to take this path to propagate it. Okay, upper one. So it means A, I am going to select the non-controlling value of the AND gate. So what is the non-controlling value of the AND gate? It is 1. So I have taken 1. If B is faulty, then does it really matter that what will be the fault-free or faulty value of A? No, it doesn't matter. So in both of the cases, I'll be having fault-free value is also 1. And if B was 1, then also it is 1 only. In both of the cases, I have the value of A branch 1, 1 only. Now I will be finding G value. G is what? Ended of both of these. So while we are doing any kind of logical operation, we have to make sure that the fault-free values are logically operated with the same fault-free value, and the faulty value, let's say B stuck at 1, we are talking about in this particular case. So that has to be ended with the corresponding B stuck at 1 of the other branch. So here the first one is 1, 0. So this is going to give me 0, means fault-free was expected to be 0. But what is the faulty value? For A it is 1, and for B also it is 1. So the faulty value becomes 1. So I'm expecting the output 0, 1. Fault-free and faulty. Let's come to the next one. If I do not want to propagate my fault through this particular branch, I can take it to controlling value. Controlling value is what? 0. For AND gate, controlling value is 0. So it means I have deactivated this particular path. So if I have taken 0 over here, there was no fault considered at F branch. So fault free and faulty, both of the values are 0, 0. Irrespective of this 1, 0, the propagated value at H is 0, 0. Fault free, first one is the fault free and another one is faulty. Now this is OR gate. If I am going to make OR combination of 0 with 0 and 0, 1 with 0, I am getting output 0, 1. So the fault free value is 0 and faulty value is 1. Means actually we were expecting that if there is no fault, the LED was expected to switch off, but it is switch on. So it means I can detect the fault. So can I say that my test pattern becomes 1, 0, 0 for B stuck at 1. This is for just B stuck at 1. Now, in this particular case, just have a look. At each and every line, you have two set of bits, means two memory elements are required. So how much space is required in the computer? You can just think about it. Now, let's say there are n number of faults. So for n number of faults, I have to repeat the n number of passes. In each and every pass, I require one fault free and one faulty, 2 bits for each and every branch. So it requires n into 2, n number of faults into 2, and let's say k are the number of branches. So these many actually memory space, this much of memory space is required for the serial fault simulation. So I hope you understood the serial fault simulation technique. So if there are n number of faults available, then we need n pass. This is the first pass for single fault. So if I want to detect F stuck at 0, I need to take care of another pass. Likewise, for J stuck at 0, I have to figure out the other pass. So likewise, this is the serial fault detection technique, which is known this of all these. So let's come to the next one. The next one is the parallel fault simulation. In the parallel fault simulation technique, what we are going to do is we are going to take multiple faults all together. We will try to activate multiple faults all together with the help of some test pattern. It might be possible that we are able to detect more than one fault, or maybe some of the faults we are able to detect. So in this particular case, there are 3 faults and we try to take all the 3 faults all together. So how many bits are required? For each and every branch, we require 4 bits. Why? 1 is the fault free and 3 for each and every fault. So 3 are reserved for each and every fault. These are reserved. And the last bit is fault free. Means we will consider FF means fault free whenever there is no fault existing in the circuit. Then what could have been the value over there? So let us start it. So the same set of faults are considered. B stuck at 1, F stuck at 0, J stuck at 0. So this is B stuck at 1. if this is stuck at 1, to activate it, what we need? This is already stuck at 1. So it means just opposite of that can activate that. So that's what we have chosen 0 as the input. Okay. This is B stuck at 1. We have chosen 0 for this. Now F is stuck at 0. So in order to activate this, what we need over here? Just opposite of 0, that is 1. So that's what it is chosen 1. Now third one is the A branch. So A branch, either you can take 0 or you can take 1. Why? Because this is B. This B is having two paths. One is taking from upper side, another one is taking path from the downside. So in both of these cases, maybe that this F1 is also going to take this path, so we can think that it may actually override that, and maybe the B fault is not being detected. So we have taken this as the non-controlling value so that I can propagate this fault to the output G. I hope you got it. I have chosen A as non-controlling value, so my value at B, the fault at B can propagate to the G branch. So first of all, what you have to do? First of all, you have to take care that in circuit, every branch is having some name, because all of these you have to write as a computer program. So for that, you should give name to every branch. Once you have given the name to every branch, then you can proceed with that at which branch, what should you have. So let us start with this. We have taken 4 bits. Bit space is 4 for each and every branch. One is fault free and other 3 are having the space reserved. First one is the reserved for J stuck at 0. Next one B stuck at 1. And the third one is for F stuck at 0. So we started with input B0, F1, A1. Since it is B0 and input we are trying to figure out, so this blue color is fault free value. Means there was no fault existing anywhere. So this 0 will remain 0 if no fault was there. 1 will remain 1 and this 1 will remain 1. Now if B stuck at 0 fault was there, B stuck at 1 fault was there, or F stuck at 0 fault was there, it really doesn't matter because it is the input. These faults are not going back and tell that, okay, you are 0, we are here, and you please become 1. No, this fault know how is troubling this. This fault is know how troubling the input available over here. So it means there is no impact of B, F, or G fault at the input B. So all of the values will be according to the fault free value. You got my point? Likewise, at the input A and F also, there is no impact of B, F or J stuck at faults. So the values are as per their fault free value. Okay. Now let us proceed. So as we are proceeding from input to this stem to this fan out branches, so this crosses this fault. So it means at place of B stuck at 1, the bit will get reversed with 1. So at C and D, you will be having this set of values. Fault free value was 0, but other values will remain like that, and this value is getting changed to 1. Now we are passing this through the inverter. So all of these values will get inverted. So instead of 0, we will be having 1, and instead of 1, we will be having 0. So this is the E branch value. Now we have to calculate G. So G is the ending operation of these. So we will be taking the corresponding AND operation. This would ended with this ended with this. So since all of these values are 1, 1, 1, so it is non-controlling. So whatever C value I will be having, that is actually is appearing at G. G branch is having all the values which were coming through the B fault propagated. So the set of values I am having over here is this. Now at the same time, I have to figure out H also. So for calculating the H, we have to do the end operation. Corresponding end operations will be like this. So the first one, 1 and 1 is 1. Another set becomes 0, 0. And last fault-free value is also 1. Now there is OR operation. So just complete the OR operation and we will figure out that this becomes over here. What it becomes? It becomes, the first one becomes 1, then again 1, then 0, then 1. So this 0 was corresponding to F. So it means F fault is being detected over here. Then we see J is stuck at 0. So J is stuck at 0 was the first value. So this is getting turned back to 0 because of J is stuck at 0. So finally the set becomes this one. Now how to identify that which are the fault sets which are detected? So in this we will be doing just comparison of the other values, faulty values with the fault-free value. When we are doing so, we will find that the last one, which was the fault-free output, this was the fault-free output. This is a differing in this case and this case. So it means we are able to detect this case, that is F is equal to 0, F is stuck at 0, and J is stuck at 0. These are the two faults we are able to detect with the help of this. Okay, so in this manner we can figure out with the help of parallel fault simulation technique. You can see that at a time two faults have been detected, while in the previous case serial fault detection technique only one fault at a time was detected. Let us consider about memory. So if we think about memory, then the memory is actually in that particular case, if there are three faults, so 3 into 2 into the number of branches, let's say k are the number of branches, this much memory was required. In this particular case we require basically there are three faults and one fault free. So total space is 4 into the number of branches k. So 4 times of k. So here we can have 6 in the case. We will try to optimize every pass so that it is find fault in detected. For example, in the previous case, the serial fault simulation, we figured out that this fault B was we were able to detect that fault. But in this particular case, I'm not able to detect all these faults altogether. So what is the problem with this? That these 4K spaces actually are reutilized so that I can also detect this fault. Okay, so for example, let's say I'm going to nullify this. So I will be having the controlling value over here, 0 over here. If it is 0 over here, so it means it is also 0 over here. And then I will be able to detect this fault. Fault available at B, I am able to detect. So it means I need to pass, uh, this is a single fault, and for this single fault, I need to make one another pass. So it means the number of passes, let's say 2 passes are there, so it has to be multiplied by 2. If we need 3 pass, then you have to multiply it by 3, and so on and so forth. So it means this is underutilization of the complete set of memory elements. So that is the complexity, and the time consuming problem is also there because more space is required and number of passes, yes, it set of number of go up to so far about. Gaurav, just check the chat box if there is some question. Let us take it, otherwise we'll proceed. Do you have any questions, sir? I'm so sorry, it was muted. So we are talking about the parallel fault simulation and the deductive fault simulation technique difference. In the deductive fault simulation, we are going to deduce the uh, list of fault values. In parallel fault simulation, what we are going to do is we are going to reserve, in this particular case, 4 bits we have taken all together to reserve all the set of faults. So every branch will have 4 bits reserved for it. For example, these inputs are having the redundant copies of the same bit. We all know that if the input is not having any fault and all these redundant bits are actually consuming much more memory space. If multiple paths are required, for example, let's say instead of 3 faults, there were 4 faults. So 4 faults will be able to cover 3 faults in one and 1 fault in the another one. So that 1 fault, because we have only reserved here the orbits are required more, hence the power consumption related is also more, right? So in deduction, what you are going to do is whenever there is a change, that change you are going to record and then only you are going to utilize the other set of bit. Otherwise, you are just ignoring it. Okay, so let's have the example related to this. Yeah, so let's have the example of AND gate. And let's take the example of A is equal to 1, B is equal to 1, and C is equal to 1 at the output. And this was the fault-free circuit. So this fault-free circuit, which type of faults it can cover? It can cover A is equal to 0, B is equal to 0, plus C is equal to 0. These are the fault sets it is able to cover. Why? Because this is the activation. A is equal to 1 and B is equal to 1 is the activation for all these 3 faults, right? A is equal to 1, B is equal to 1 is the activation for all the stacked 0 faults at each and every branch. So we will be taking all the branch faults available at A plus B plus C stacked 0. Okay. Another case, if we are going to take, let's say A is equal to 1 and B is equal to 0 case we have taken. So output of the fault-free circuit was expected to 0. So it is going to cover LA list at A minus LB because we have made it 0. So B is controlling. B is going to control. So if any fault was available on A branch minus B branch plus C stacked 1 will also be available. And likewise, if we are having both of the inputs as controlling 0, 0, then the intersection of LA and LB we will be taking plus C stacked 1 because output is 0. So it means if C stacked 1 is there, so output will become 1 and that's what we are able to cover that. If you think that it is not able, you are not able to understand this, I can repeat it. Otherwise, with the help of example, you will able to understand it in good way. So remember, if non-controlling values are there, for example, in case of AND gate, non-controlling values are 1, 1. Non-controlling values are the one which will not affect the other input. That is the non-controlling. For AND gate, if I'm going to apply 1 over here, then the input over here is going to decide what is the output. So 1 is the non-controlling. Likewise, for OR gate, 0 is the non-controlling value. So whatever I have, 1 over here, just replace that with 0 in the OR gate and the same formula will be utilized for that. Okay. So let's take the example. The same example has been taken for the deductive fault simulation technique. So in this, the same set of faults are considered. B is stuck at 1, F is stuck at 0, and J is stuck at 0. So in the previous case, what we did is in parallel fault simulation, we reserved 4 bits each for these 3 faulty and 1 fault free. This was fault free. And these 4 bits were reserved for each and every branch. So it was exponentially increasing the memory space for one particular pass only. Now what we are going to do is, if we see that there is no change, we will not reserve any bit for that. Only single bit will be okay. That was the previous case also, right? So let us start. We have taken the same set of inputs. Since it is B stuck at 1, so to activate that we have taken it 0. This was F is stuck at 0. So to activate this, I have taken F is equal to 1. And since I want to pass this fault to G, so I have taken A as non-controlling value. So the input set becomes A is equal to 1, B is equal to 0, and F is equal to 1. This is my input set 1, 0, 1. Okay. Now let us proceed. So for each and every, we have to write a list. That list will be containing only the faults available on that particular branch. So for example, I want to find out LB, list of faults available on B branch. So B stuck at 1 is the fault available on B branch, and the same fault is available is there, that fault is being propagated at C and D also. So LB is equal to LC is equal to LD, and this is going to contain only one fault, that is B stuck at 1, right? Now let's go to LA. LA is not having any fault, so LA is equal to 5, means no fault is available. Okay, that is 5, empty set. And likewise, LF I want to consider. So LF is having F is stuck at 0. So LF is this. If I want to consider LE, what will be my LE? Yes, please tell me. So look at this. The LB B is stuck at 0 is going to propagate over here. So this will be equal to LB. If I could have another fault available over here, then depending on what was the input, I could have taken that also into consideration. So this is LE is equal to B stuck at 1 in this particular case. This is B stuck at 1. Now we will consider this one. So have a look at this. This is 0. Inverter of this we are expecting 1. Input of AND gate 1, 1. What was the formula? LA plus LB plus LH stuck at 0. So LH stuck at 0 is not available, but yes, LA is something, LB is something. So both of the faults will get added in order to figure out LH. So LH will be B stuck at 1, comma, F stuck at 0. I hope you understood this. Likewise, let us consider this one. In this case, you have 1 over here and then plus 0 over here. So this 1, 0 case is there. Okay. So we'll be taking 1 minus, if something is common, that has to be reduced, but there was nothing common. So if nothing is common, it means the LG will have the same fault. So LG will get propagate this fault. LG is equal to B stuck at 1. Now let's come to the last one. This is OR gate. This OR gate is containing what? This was 0 value. So this is going to propagate 0. This was 1, 1 value. So this is going to propagate 1. So one set is 0, 1. It is having. So it means what I have to do? I have to take intersection of both of these. No, I have to reduce that fault, right? So maybe LH minus LG I have to do. LH minus LG. So what does it mean? It means and plus, because output is expected to be 1, so plus J is stuck at 0. So this will be the LJ, the folds at LJ I will be having it this way. So what it is going to give me? It is going to give me this set. Yeah. So this was my LH, this was my LG. When I am making LH minus LG, so this B1 is getting cancelled away and I am left with F0 from here. So I am getting F0 over here and J0 because it was there at the output. So only 2 faults are being detected. So this is my fault simulation technique for multiple faults all together, and it is going to detect two faults altogether, F0 and J0, right? So these are written over here, F0 and J0 are detected. Yes, I hope you got it. Yeah, so in this case, we have not been able to detect the B1. So now let us figure out how we can do it. First of all, let me explain how it is better than the parallel fault simulation. So in case of parallel fault simulation, at each and every branch, you were expecting uh, 4 of the bits. Here also 4 bits you need, 4 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of branches are 9. And for those 9 branches, 9 into 4, 36 number of memory cells were required for single pass, right? In this case, what we are going to happen, I do not require anything for A because there was no fault at A, right? I just require one bit space for this because only one fault, one bit space for this, one bit space for this because only one. So this is one, LC, LD only one, LF only one, LE is also one, LG is also one, LH is 2 number of bits, and LJ is again 2 number of bits. So in case of the previous case, there were 36 bits required, 36 cells, memory cells were required to detect the same set of 2 faults. But in this particular case, let us count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 bit cells are required to detect the same set of faults. So you can see the memory is reduced multiple times. The memory has been reduced, and that's how the less memory consumption is going to happen when we are going to implement this deductive fault simulation technique. So in the same technique, let us consider how the B fault can be detected. So in order to detect the B fault, let us take to change this from 1 to 0. Basically, what happened in the previous case, if you visualize, when we reached over here, we saw that this was 0 is going to change to 1, and this becomes fault free 1. But this was actually 0. No, this was actually the containing fault B. Actually, it was 0, but it was having the fault B. It was containing fault B. This was also containing fault B. So when you are taking LH minus LG, then this fault was reduced from both of the branches because it was common in both of these. It is the case similar. Yesterday, Professor C.K. Ravi Kumar discussed that it was when A is taking inverted and non-inverted combination, and that is given to OR gate. So it is the similar case. So that fault is never being detected, right? So it is the similar case, and that's how it is not being detected. So in order to detect that, here we have the extra circuits and gate. So what we are going to do, we are trying to force this A input to 0. Instead of 1, let us transit it from A to 0. So let us see the effect of this. So if I'm making it 0, what is going to happen? Forcefully, I'm going to make the output of this to 0. It means LG is 5. What is LG? LG is not having any fault over here. You got my point? Previously, LG was B stuck at 1. Through this, LG was B stuck at 1. But in this particular case, I have LG is equal to 0. LG is not having any fault list. Okay. So here, previously also it was 0 and it was 1. So in 0, 1 case, fault free, what we have, LH minus LG will be taken. It means LH directly is going over here and plus J is stuck at 0. So LH is directly going at the output along with J is stuck at 0. So what was LH? LH was already containing two folds, B1 and F0. So what will be LJ? LJ is containing all the three fold sets. B is stuck at 1, F is stuck at 0, and J is stuck at 0. So all three folds are detected with the help of a single pass. And that bit pattern is the test pattern. You have to make a note of that because you have to choose the test patterns in such a way that the maximum coverage is possible. In the previous case, when you selected 101 test pattern, out of 3, only 2 folds were covered. So the test coverage was 66% in this particular case. Okay, but in this particular case, if you have changed it to 011, then 3 out of 3 folds we have covered. So the test pattern coverage is 100% for this particular diagram. I hope you got it. Shall we proceed? Gaurav, please let me know if there is something in the chat box, some question is there.
Yes, ma'am.
Yeah, please. What's the question?
What is L here? Is from Sai Kumar.
Sorry, what is?
L.
L is the list of folds at that particular branch. For example, I am talking about LB. LB is the list of fold sets at that particular branch. This branch, L is the list of folds that can propagate through this branch, that is LB. LH means list of folds propagated through this branch is LH. LJ is the list of folds propagated or detected at this particular branch is LJ. I hope you got, Mr. Sai Kumar. Any other question, Gaurav? Thank you. Any other question, Gaurav?
No, ma'am. Actually, it was 1207 from Aditya sir. Ma'am, C/0 in case 1, Y in equation, and so on.
Sorry, can you repeat it?
C/0 in case 1, Y in equation, and so on. Only that much, ma'am.
C/1.
C/0 in case 1.
In case 1, which case? Can you unmute him so that he can ask what is the issue? I'm not getting this one because C branch, the fault propagated from B is only available. Can you unmute him so that he can ask?
I will send him a request.
Yeah. So by that time, if somebody else is having some question, please feel free to ask. Okay, if he is not available, let us move to the next topic. Fine. So the next one is the concurrent fault simulation technique. So here, what was the benefit? So the benefit was that instead of, see, first of all, we have detected all three faults altogether with the help of changing in the test pattern. So the test pattern, instead of 101, 1 is A, then this is B value, this is F value. What we will be using 0, 0, 1. And my test pattern, using this test pattern 001, I am able to detect all these three folds, right? What is the other benefit? Instead of using 4 bits at each and every branch, that was going to give me total 36 memory elements to utilize, or the memory space to utilize. What I am going to do here, for line B, I just need 1 bit, F, LC, L, just 1 bit, E, just 1. quiet and much robust. So the memory space will reduce drastically. Now let's come to the concurrent fault simulation technique. So the concurrent fault simulation technique is also the technique which uses multiple fault simulations altogether. Why do we need the multiple fault simulations altogether? This circuit is a very small circuit, right? Here only three very basic gates are there. But if we are talking about real-time chips, so real-time ICs or chips, it is having millions or billions of transistors or the logic gates altogether. So this is really very difficult to run the serial fault simulation for each and every, because then there are along with those there are multiple levels also. So yesterday we have discussed the structural and the functional testing, that there are multiple levels, then the number of faults will get, number of fault size will get increased, and then the total number of faults will be increased by the number 3 raised to power 3 raised to power k minus 1, where k is the number of fault sites. So it means this is very complex. So serial fault simulation will work for the bigger circuits. So the only algorithms which can actually afford multiple fault simulations altogether are the solution. So the parallel fault simulation, because it always reserved one fault free in other faulty spaces, so it requires so it requires actually multiple spaces. It requires some process. But we do realize dynamically we will be taking the spaces and what so this was the dynamic one. So, in deductive fault simulation. So as and when there is required space, we will be taking for each and every branch. One bit is required, we are just taking one bit out of that random memory. So dynamic memory allocation is going to happen in this particular case. That's what we are able to reduce. There is no previously reserved chunk of memory. So from computer architecture point of view, it is going to give us the benefit. So like this, there is concurrent fault simulation technique. So in concurrent fault simulation technique, how it is going to work? First of all, it is going to simulate multiple faults altogether. What happens in this? Each gate retains a list of fault copies, each of which stores the status of the fault exhibiting the difference from the fault-free values. Simulation mechanism is similar to the conceptual fault simulation, except that only dynamic difference means fault-free circuit is also retained. It is very versatile in circuit types and gate delays as well. Although theoretically all faults in the circuit can be processed in one pass, but the memory explosion is a very big problem, because multiple memory elements will be required to retain each and every copy. What does it mean? Copy means, let's say there is AND gate. So for example, this is AND gate. So in this AND gate, what I need, I will be having one fault-free copy. This is fault-free copy. Let's say inputs were 1, 0, and output was expected to be 0, that is 0. Okay. Now, where can be the fault possible? Fault is possible at this branch, or this branch. So three faults are available. If the fault is available at the output, what is the output expected? 1. If the fault is available over this input, then the output is expected to be 0, that is equal to your fault free. If the fault is available over here, then the output again you will be expecting 1. So here you can see that this was the fault free copy. The output of this is matched with these three, and you will be able to see that this is going to match with this. So it means it is this fault, this particular fault, this stuck at 0 fault is not able to be detected by this test pattern. So yeah, so let us take this is actually the dynamic equation only. In this, we will be having the faulty and fault-free values for each and every gate. So the denotation is somewhat like this. This SAT is representing the inputs and the other SAT is representing the outputs. And the very first one is the fault-free. This first one, which is having nothing just before this is the fault-free pattern for that particular gate. And the next one is corresponding to the faults available. For example, for B stuck at 1, how it is going to change. For F stuck at 0, how it is going to change. For G stuck at 0, J stuck at 0, how it is going to change. So as in when the fault is getting propagated, you can see the memory allocation is more. For example, LJ, how much memory it requires? It will retain this copy. This is 0, 1, slash 1. Fault free, 3 bits are required. Again, if B stuck at 1 is also propagating through this, so another 3 bits are required for this fault. Another 3 bits are required for this fault and another copy of the gate 3 bits are required for this fault. So in this fashion, this covers all the faults available and it retains the copies of all faults. So it is simulating all faults in one. Okay, let us understand how it is going to work. So we have taken the same input test pattern 1, 0, 1. 1 is the input, this is the input at A. This 0 is to activate the B stack at 1 and this 1 is to activate F stack at 0. So first of all, see this is 0, right? There is no gate over here. There is no gate over here because this was a fault free value was 0 and the faulty value was 1. And likewise, fault-free value was 0 and faulty value was 1. So we will keep this in mind while applying for the gates. We'll only retain the copies for the gates. Like this was the branching, right? So for this, we have not written LA, LC, LD, LF. We have not written. Why we have not written? Because these were not the outputs of any gate. We are only concentrating on the gates, but yes, the replica of those gates with the faulty and fault free values we have to put, right? So yeah, that's the thing. So let us proceed with the first gate. The first gate's output is LG. What is the output? This is LG. So what was the fault free value? Fault free value was input here is A and input here fault free was 0. A is equal to 1 and equal to 0. So that's what LG 1 0 and 0. That's the true output for output fault free output. Okay. Okay. So how many free output can we having? What's available? So that's 1. So, okay. If this output is possible, then output is how many fault ones are visualized is one output of this. Faulty or how many fault is one is output into how this is be stuck at one the faulty expect so expected to and this is the at the reverse of what and G faulty and that even is now let's do the fault developing both expected to be more next again each output second one gives us just two one faulty output was expected to be B is second inputs and outputs. So let's go to the next bit. So we are having the output L. To the next bit. Two B and another is F. B zero G. So the fault free must be input given there. This one is going to give one dash. If both one zero. Zero eight and yeah, B. So please avoid this one. Avoid this one. B. So all if you have like this with the finally you will be as possible. Right? Yeah. Example so now the fold in this actually we are not able to get this code, right? And if I'm changing this pattern to G, another one, and this is simulation concentration. I'm doing this pattern and So end is always so what is simulation? When we can detect it. Sorry. For example, this is detected. For example, we whatever fault you have, that figure out that we detect V is equal to 1 is available.
Hello, ma'am.
Sorry. Figured out that we fault at
Ma'am, actually, your voice is breaking.
Is there any question? Voice is it clear now?
It is now. It is
Yeah.
now. Yes, ma'am.
Oh. That is telling me if there is some query, you get you. So basically, what is it? B, but I'm not able to get it. It means I start. I was able to detect with that particular approach. Type of this is so this is able to detect change and line so and you are confident. So first activated. So that particular fault, for example, can be activated. B stuck at 1 can be activated if I make making it 0. What are the other inputs? A and F. How many combinations? A and F can combine. A 0 0. This these are okay. These are negatives. I'm going to the B. I'm going to make it output together. This is also all to be also. This I'm getting 0. I'm able to my getting 0. So it means this type cannot have. Cannot have. Basically, and hope I will see whether I can have. So this parts I can have. Let's go. Okay. So parallel simulation technique is so parallel fold simulation, parallel pattern simulation. So in this parallel pattern simulation, yeah, some other fault is taken, but let me give you the example of this fault B only, okay? Because you are aware about this fault, yeah. So I have taken this circuit. So this was the fault. I have taken the pattern instead of writing like bigger kind of bracket. I will just write it in this way. Like 0 at the input means this is 0 at the input. So 0, 0, 0. For all fours, I am having it 0. So there is only one fold, right? So other inputs will be the patterns. One is the fold. So this is, let's say the first one is B stuck at 1. And all other are actually the patterns, the combinations. So I am having, let's say, total 3 patterns. We figured what happened. So, I need with B zero. I have the area as I'm going to define for this first B. So one is B. The first B is no after this. Going to one goes right. Going to back to and then I will have zeros. This my this is another all of us energy another one. The first needs B is to get 0. So with B is to get 0, I have yes. So this in this way, I will make the pattern, and B is to gives me 1 here. So this 1 is getting propagated. This 1 is getting 1 at 0 here. So the free and faulty combinations for B branch, I will be propagating to this, right? So the fault free was 0 only. This is getting 0 slash 1. This is getting 0 slash 1, and likewise. Now I have to check for each and every test pattern. So after checking each and every test pattern, I will be finding at the output that with the help of 0, 0, 1, I'm able to detect my fault. I'm able to detect my fault. Instead of the other two combinations. Yes. The other example, the two combinations. Yes, I see the other example. At least I can see. So fault one, and the faulty copy for that particular phase is the double one. And this fault copy acknowledged. So read the double. By comparing this will achieving the respecting for these two, and you will be able to figure out which particular for your pattern detective. The first one, the which was the upper and one is the one. So the upper one is having 1 and lower one is having 0. So it means this particular pattern, the pattern becomes 1, 0, and 1. This pattern we are able to detect this F fault. Okay, with the help of this pattern we are able to detect this F fault. So likewise you can run this for J is equal to J is check at 0 as well, and you will be able to figure out that with the help of the same pattern you are able to detect J is check at 0 as well. So this is parallel pattern simulation technique. Here we can see for one fault multiple space for each and every branch. The first spaces is to here for store the patches is to have taken into consideration at the date. This will be recorded there. It is so the fault then the fault over here, the fault was used the first like set of from here and B, and as it propagated is so we will technique more. Probability that is we have to be able to figure once the pattern data to detect the fault is more as compared to the previous anyone technique. Yeah. So the next one is the critical path tracing. So critical path tracing is very important. Critical path tracing means you are going to trace a path which is critical to that particular circuit, logic circuit. So critical path tracing here, what is critical? Critical thing is the fault. Whatever fault you have, that is critical. So that fault, if you can propagate at the output somehow, where you can observe only at the output, right? So if you are able to observe anything at the output, any fault at the output, that path particular is the critical, and the gates coming into that particular path are critical gates. So this is what it is written, what it is in this information. So we detect faults at the fan out free region. So this B can go through this. It may take this path. So since it is going to take this path, so along with this gate becomes critical. So we have to take this also the critical one. Okay, this is the input. This was actually faulty also. This line F was faulty also. So for that purpose also it is critical. So basically this critical line, what faults it is going to make sure that these are the critical faults which can be detected through this. Let us figure out. So we started with B stacked 1. So this B stacked 1, make sure to detect D stacked 1 and E stacked 0. E stacked 0 means you are having because the output is coming is also all these set of faults, this path is critical. Okay, sensitive inputs, and these are the critical lines. Okay, now if you are only considering or stuck at 1. So for B stuck at 1, there can be two critical paths. It can see our job is to push that particular fault. Okay, what is our job? This is the input. Fault can be anywhere. For example, the fault is here. So my job is to push this fault at the. So in order to push that fault at the output, I need to go through some gates. I have to make sure that the other part of that particular other inputs of that particular gate are non so the effect that fault can propagate at the output. So this has to be non-controlling. This is AND gate, so non-controlling values. So keep this value. This is OR gate. I'll keep non-controlling value 0 for this. And likewise, I have to make sure and I have to try to propagate this fault at the output. That's what I do. And in this journey, whatever number of lines or number of gates I will be having, those are the critical. The set of all these is the critical path. Critical lines in this particular thing. Both of these paths for B stack at 1 are critical, right? So this is the critical path tracing. Any questions so far? Please Please take my name or ask if you have any question. Yes, do you have any question?
There are no questions in the chat box as well, ma'am.
No questions in the chat box? Yeah, I was just looking at it. So, yes, today evening 6 p.m. we will be having the other session. In that session, I'll be covering the different fault. Uh, uh, yeah, Boolean difference. Yeah, what we difference combination combination of ordinal logic force in this section, which will be within the automatic pattern generation. Which is using that and yeah. So yeah, we will be covering that first, and after that we will be going to the scope measures. That is really very important. So I think we should conclude the session for the day. It is already 1 p.m. Uh, I would like to take the session. Maybe I can extend half an hour more if participants feel okay with this, because it was not your fault, it was our fault that the session couldn't started at the right time. So that's why I do not want you to forcefully stay back for half an hour more. So what your opinion? You may type N in the chat box if you want that we should conclude the session. You may type N in the chat box if you want we should conclude the session. I think they are tired now. We should stop because it is already 4 hours. It's been there. So Gaurav, please stop this recording and let's be ready for 6 p.m. in evening sharp. We'll be having 6 p.m. in the evening. We'll start the session. So I'll try to cover a little more. Okay.
Yes, thank you so much, ma'am, for your
Okay.
time and
So
for sharing such insightful thoughts. Thank you.
thank you so much. Thank you. So, yeah, let us meet 6 p.m. sharp in the evening. Please do not get late. We'll start the session at 6 p.m. Sharp in the evening. And 7 p.m. we have another session from Mr. Harsahai Jaiswal. He is from Ostrom, Austria, and he will be giving you the glimpse of advances in reliability perspective. He is having very good industrial experience, so definitely it is going to be helpful for one and all. Thank you so much.
Thank you.
Okay. Yeah. Bye.